So the title of my presentation today is the material specifications for additive manufacture. And I think following on from Martin's talk, it's probably a nice joined up sort of presentation really. So we're going to go into more of the practicalities because we are a metal powder producer. So I don't want this presentation to be an advert for Wall Colmonoy, but just take you through a couple of slides to say what we're about, who we are, where we've come from, and maybe some of the heritage that allows us to be able to deliver these powders of high quality. Before we move on, a little bit of a background. You know, I'm an alumni of Swansea University as well, Martin, so maybe we should catch up at some point on that one. Certainly been with Wall Colmonoy for a year now, so that's my first introduction really into powder atomization and powder manufacture, although I had some experience obviously based in the materials world of a long introduction to powder metallurgy. So it's an interesting challenge to come into the manufacturing side of the business. Okay, so next slide please, Pamela. So just an overview of what I'll be talking through today, give you an idea of who we are, what equipment we're sort of focused on delivering powders for, and some of the practical aspects in terms of what alloys are out there, what PSD requirements, that's particle size distribution, are required for certain technologies, some ideas in terms of what the particle shape can be, and how we manage to manufacture those through our processes, and some of the restrictions that are in place which drive the economics, and ultimately, you know, following on from Martin's talk, how we have a look at the quality of the powders. Next slide please, Pamela. So before we started today, we had a conversation about where the name comes from, and it's an interesting one. I think some out and out scientists got together and probably sniggered about the name really, but so AF Wall bought the patent for a new alloy, and the alloy was formed by two metallurgists, Cole and Edmonds. So Wall, Cole and Edmonds, and the alloy that they made became the name of Wall Colmonoy, which it's taken some practice over the last year to be able to say it without tying up myself, but yeah, it's an interesting sort of acronym, and obviously some history in that one. 1938 it seems a long time ago now, and Wall Colmonoy are pretty good at inventing the technologies that we use day to day in terms of joining stainless steels together. Next slide please, Pamela. So our headquarters is in Detroit. Madison Heights is on the outskirts of Detroit in Michigan, and we have a European headquarters here in South Wales, based in Pontardawe. So here in Pontardawe, we supply most of Europe, the Middle East and Africa. We do have reach into China and Japan, but that's a shared territory with the US business as well. So quite a global company. Next slide please, Pamela. I'll whiz through these. So we celebrated 80 years from the US side of the business. It's a little less than that in the UK. We've celebrated, I think it's 52nd year now. So again, quite a long heritage, quite a long involvement and interaction with metal alloys and their development. Next slide, please. So here in South Wales, decent sort of installation. Again, it's been here for 52 years now, and it's a good turnover, £33 million in sales, mostly metal powders, decent size footing, and a decent employee count of 215. And we have three combined business units. The alloy products division is where we make our metal powders, which is most relatable to today. We also have a precision components department, which produces machined cast metal parts. And we also have an aerobraze engineered technology division, which supports coatings and part manufacture for aerospace. Next slide. So this is our vision. We aim to be the global leader. I think that's a mantle we owned quite extensively, really, from the start of the world's progress through stainless steel brazing. And we aim to take that forward really into additive manufacture and other areas as well. So we try to make metals work harder is our strap line. So next slide. Again, I've touched base on some of these, some images really to show you what we're up to. So we are a global materials engineering company. So you can see some of the coating technologies there, some of the parts that we produce via our business units, and some of the ways that we can do some novel coating on certain materials in aerobraze. And that nice image you see in aerobraze is a high velocity oxy-fuel coating manufacturing process. Next slide. Industries wise, it's very spread out. So you can see a lot of images there in terms of aerospace, transportation, defence, paper and packaging materials, and the glass industry. And you know, in these days of global pandemics, the glass industry is seeing a resurgence. Really, it's most people making their own food at home because they can't go to restaurants. Has seen an increased volume of sales for us in the glass industry, so that's good. That kind of balances out some of the negative visibility really of the automotive sector, and that's been severely hit by the pandemic. Okay, next slide. Again, some nice images. What we supply, we got some trade name materials. We celebrate sort of a long heritage really in Colmonoy, which was one of the first alloys we manufactured, which is nickel based, and coming behind that quite quickly was the Wallex grades, which are cobalt based materials. And we also have obviously tailored materials then for different processes for nickel brazing and copper brazing. Next slide, please. So today, additive manufacture, you know, in terms of supplying powder into that industry, we're looking at the four main areas of technology, be it laser powder bed fusion, DED, electron beam melting, and binder jetting. And on the next slide, you'll see some people that we're working with and in contact with in terms of supplying powders and testing our powders and qualifying our powders again to ASTM standards in those technologies. Next slide, please. So those areas, and there's probably a lot of people on the talk today that could probably make this list much longer, but certainly the alloys that those technologies use can be seen here. TI64 has been mentioned already today. Aluminium powders, whether it's alloyed with silicon or not. Cobalt chromium powders and cobalt-based alloys, and the general sort of pretty well understood stainless steels, 74 pH, 316, some tool steels, and nickel family alloys. They're all able to be manufactured via the processes we have at Wall Colmonoy. Next slide. It's maybe not so clear. So certainly one thing I wanted to talk about a little bit more in detail today was powder particle size distribution. So alloy specifications are pretty much there. They're well understood. They're quite old. Some of them. Some of the tool steels obviously a bit older, and we tend to work within the confines of that designation in terms of the alloy chemistry. And you know, it's certainly able to we're able to melt and combine many different raw materials together to be able to define new alloys, to make any sort of adjustments to any of the normal alloys like the 316s to make them more suitable if that's needed and increase the performance of the parts. We're zooming in here. So basically, in terms of powder particle size, generally the technology seems to be defining its own particle size distributions. So certain technologies will define and require certain distributions of the powder particles. So you can see there, thanks for trying to zoom in there, Pamela, the electron beam melting uses a coarser grade of powder. You can see from 45 to 106. Laser cladding uses 45 to 75. Laser bed fusion uses 45 micron particles down to 15. But these are in development. You know, it's all quite a new topic, a new area for everybody, and certainly because we are in contact with the end users, we tend to have those discussions about issues that may be being experienced in the manufacturing process. So certainly powder flow and powder characterization is key to this, and understanding the range of materials within those set limits. So, you know, a powder particle size between 15 and 45 for selective laser melting doesn't mean that there's an equal amount of every particle between 40 and 45. So it's a process which atomizes metal using either gas or water, and you get obviously a spread, a distribution, a Gaussian distribution of the particle sizes within a certain range. You can affect that range, but obviously you get a spread of those particles, and it's that randomization of the atomization process which gives you that spread. And so what we have to do as powder manufacturers is to select and take away the particles that we want, that we call product, and leave the remainder, which is left to revert itself back through the process to be changed again. So that revert material goes back for another melting process and another atomization process to turn more of it back into product. So on this slide, you can see that, you know, MIM powders, again, there's a long heritage of MIM. It's been going for a long time. Very, very well understood, and they have their own particle size specification, minus 38 microns typically. Binder jetting is evolving to be minus 45 plus 5, and again, I wanted to get across today that those areas, those sort of hard stops that you might think 45 microns and 5 microns means, is not such a hard stop. We end up with a tolerance on that level of a certain fraction of the main powder, less than 5 or more than 5 in the case of binder jetting, or more than 45, sorry, in the case of binder jetting. So it's working on those particle size distributions to get the best performance and the best economics to the powder, and I'll explain that later on. Next slide, please. So for those that maybe haven't seen some of these images, I've got just some representative images of powder particles and some ideas maybe to get us all to understand how we arrive at those. So you can see in the 4 images some irregular particles that have been water atomized, and some more spherical gas atomized powder particles as well. These are iron-based powder particles. And I selected iron-based because you can see that when you do water atomize, you form a very irregular particle. And that's not always the case. Water atomization can form spherical particles as well. So basically, in the atomization process, you can see the sort of pictogram on the left-hand side indicates the breakup of a cohesive metal, a molten metal stream, having time to either spherize, to use its surface tension forces to pull itself back to a sphere before it cools down. And in water atomization, that time is significantly reduced, and you end up with the solid particle not able to pull itself back into a sphere. And so we can dial these shapes up. There are most additive manufacture tends to go for spherical, for flowability, but certainly in other aspects, irregular powder particles is the target because of maybe the reduction in necking forces for press and sinter operations, for example. Next slide. So we can see as well in terms of powder flow, I've identified a satellite particle there. So that's a smaller particle that's stuck to the body of a bigger particle. You can see quite a few examples of that there, with obviously the satellites being very, very small usually, but some slightly bigger as well. Next slide, please. I'll describe how those are formed. So in a gas atomization process, those satellite particles are formed via the natural breakup of the liquid metal stream. So as I said before, the distribution of the sizes that we get in the atomization process allows some very, very small particles to be made, and they tend to be more buoyant in the convection and turbulence forces within an atomization tower. The image you can see on the slide is an atomization process. And you can see that the powder particles from the tipping furnace at the top are channeled through an extraction process, collected in a powder hopper, and the exhaust gas flow, if that's matched with the atomization pressure and flow that results from that, we end up with a steady downstream of powder particles through the process. But it's very, very difficult to control the turbulence within that tower because of the interaction of a gas stream with the liquid metal and the resulting large increase in volume that gas experiences as it gets hotter. So that those turbulence and convection forces can make those smaller particles return back to the top of the tower, and that's where they come into contact with the particle, which is solidifying at a slower rate because of the mass of the particle. And so that attraction and that connection can result in those satellite particles. So powder flow. So one thing I wanted to talk about was we end up with very, very fine grades of powder in additive manufacture, and the flowability can be affected by satellite particles, as we said, but even very, very clear non-satellited powders can have difficulty flowing when we're talking about very, very fine powders. So it is something to consider, that it's easy to meet a specification of maybe 45 microns down to 5 microns in terms of a powder particle size distribution. But sometimes it's difficult then for us to offer that as a flowable powder, because the material doesn't want to flow. It bridges when we try to flow it, and that perception of material flowing into a laser powder bed fusion machine or any other AM technology machine is sometimes a challenge. We do have opportunities to use flow additives. I think there's Martin might be able to guide us there in terms of a specification for using flow additives in AM powders. So that can be used, and we're working with one of our AM customers to do an investigation into the use of flow additives without the deterioration of a part, and that's in a cobalt chromium powder. Next slide, please. So, as I've said before, we need to make sure that all of the powder particles are within a certain range. We do that by what we call screening. So we try to target a D10, a D50 and a D90 value. That means that a D10, 10% of the powder particles are less than that size. D50 is the median value, and D90 is 90% of it are smaller than a certain size. It does provide challenges. The image on the right is a blown up version of a nylon screen. So you can see that there's holes there that the powder particles have to fit through. The screens you can see here are about 150 micron screen with some variation you can see in some of the sizes. So they range from 145 to maybe 163. And this is a well-known manufacturer of screens. So sieving requirements for additive, and again, some of the economics that are in play here. The yield that we get on a very, very fine fraction, be it 45 to 15 for laser powder bed fusion, sometimes is only 25% of the whole of the atomized distribution, and so the product is only 25% of the volume of the material that we've atomized. So obviously there's some production costs that have to be borne by that yield of powder, but also we have process bottlenecks is probably the best term in terms of the open area on a screen. So the amount of hole compared to the amount of nylon that makes the screens reduces as we reduce the size of the powder that we're targeting, and therefore we have to reduce the feed rate and the speed of sieving to be able to capture that powder. So those are the sort of economics and driving the economics of AM powder manufacture. We can do lots of things to help that sieving efficiency and throughput in the process, but certainly it is a factor to bear in mind when we're looking at trying to control very, very tight particle size distributions for maybe post-part analysis, that it's worth bearing in mind, guys, that the economics are going to vary. If the yield goes down because the range is getting smaller, then the cost of the powder is going to go up. and maybe the rollout of additive manufacture to the mass market is going to be hampered or slow because the obviously part price is going to go up as well. Next slide, please. So after we've done all of the processing, we've got quite a suite of techniques at our disposal to ensure that the powder meets the characterization requirements via ASTM standard or a customer's own standard. So we've got lots of different techniques to measure chemistry or the particle size distribution itself. Particle size on the bottom right is via a microtrack particle size analyzer, and we have a number of mesh sieves as well that we can do a sieve stack analysis via certain standards as well. We also look at digital microscopy for particle shape, and we have a Malvern morphology piece of equipment which allows us to measure circularity and convexity, any other characterizations really in terms of shape. There's an SEM that we can look at the surface chemistry and able to sort of quantify any issues that are prevalent with the powder, and even look at powder that's come back from an end user for regrading or recycling, and quantify any deterioration in that powder in its use. We also do some very quick, so back a slide, sorry. We also look at, there we go. I also look at doing 3D printing ourselves. We have polymer 3D printing, and we're looking to invest in a metal 3D printer in the coming months as well, to be able to qualify our powder before it ends up in our end users. So we certainly have contacts that use laser powder bed fusion, and we're looking to get a binder jetting facility in-house as well, so we can qualify all of those quality powder aspects and wrap them up in a performance characterization report before it leaves our doors. So next slide, please. That's about it from me, really. But just to sort of say that, you know, we're here, the door's open. We're able to define new alloys, work on existing alloys, define new specifications for what those particle size distributions need to be, and to try to drive the industry forward to be using the most efficient product that we can. So after that, next slide, please. I'll turn over to Pamela. That's it from me. Thank you very much for listening. I'll answer as many questions as I can.